So in this video, I have selected some worksheet questions of classification of elements and periodicity in properties, that is simply periodic table chapter. So we'll discuss worksheet questions one by one. These are important models for competitive exams. First question, the successive ionization energy values from first of an element are given. That is ionization energy values are given 801, 2430, 3660, 25,000 and 32,800 kilojoules per mole respectively. So from this we should find the element. See here clearly these are I1, I2, I3, I4 and I5 values. So clearly there is large gap between I3 and I4. That means it is very difficult to remove fourth and fifth electrons. Therefore, there should be 3 valence electrons. Therefore, the elements belongs to third A group or 13th group. Third A or 13th. So, in given options, boron belongs to third A group. Therefore, option A. Simple question only. So, this is based on the gap between ionization energy values. 3 valence electrons. That means element must belong to third A group or 13th group. In options, boron is there. Therefore, option B. That means boron, option A. Next one. Arrange the following in increasing order of ionic radii. So here given species are O2 minus, F minus, Na plus and Mg2 plus. So all these are isoelectronic species. Isoelectronic species. So we know in case of isoelectronic species, see here atomic numbers 8, 9, 11 and 12. So atomic number increases in this order. Atomic number. Therefore, size will be in this order. That means as the atomic number increases, size decreases in case of isoelectronic species. Therefore, this will be the order, decreasing order, or we can write Mg2 plus, Na plus, F minus and O2 minus. This is increasing order. Therefore, option A. Related to isoelectronic species. In case of isoelectronic species, as the atomic number increases, size decreases. Next one. So, which of the following set of properties gradually decreases along a period? Along a period, take first option. Ionization energy along a period increases and atomic radius decreases. Option B. Metallic nature decreases and atomic radius also decreases. Option C, electron affinity increases and electronegativity also increases. Option D, valency increases and oxidation potential also increases. Therefore, according to question, in option B, both are decreasing. Therefore, option B, metallic nature and atomic radius decrease along a period. This question is related to periodic properties. Next one. So this is very, very important regarding lanthanoid contraction. So identify correct statements for lanthanoid contraction. So here option A, covalent properties of lanthanoid metal hydroxides increases from lanthanum to lutetium. We'll explain option wise. Option A. So lanthanum hydroxide LaOH thrice, lutetium hydroxide LuOH thrice. So because common oxidation state of lanthanoids is +3. Since oxidation state is +3. Valency 3. So from lanthanum 2, that means La3 plus 2, Lu3 plus size decreases due to contraction. So lanthanoid contraction is due to poor shielding effect of f orbitals from lanthanum to lutetium. So size decreases means lanthanum is having more size, lutetium is having small size. Large size and small size. So as the size of cation decreases, covalent character increases. Size of cation decreases, covalent nature increases. So therefore option A is correct. Covalent nature increases from lanthanum to lutetium due to decrease of size. Next, option B. The chemical reactivity decreases from lanthanum to lutetium. So this is also based on size. Size of cation decreases, loss of electrons also decreases. As the size of cation decreases, loss of electrons also decreases. Therefore, chemical reactivity decreases. So in case of metals, reactivity directly proportional to loss of electrons. Option C. So lanthanum hydroxide is more basic than lutetium hydroxide. That means in case of lanthanum hydroxide, there is more bond length between La and OH when compared to LuOH. So it can release OH minus ions very easily. Therefore, more basic. More basic due to more bond length between lanthanoid element and OH minus. So in case of lanthanum, OH minus ions will be released very fastly. So this will be less basic. Next, option D. Option D, we know from 3D to 4D series, size increases, and from 4D series to 5D series, size remains constant due to contraction. So here zirconium belongs to 4D and hafnium belongs to 5D. So radius will be same. These two will be having almost same radius due to lanthanoid contraction. That is A correct, B correct, C correct, and D also correct. What about E? Separation of lanthanoids from one to another is very easy. So due to similar size, separation becomes very difficult. But here it is given easy to separate lanthanoid ions. So E is wrong. Therefore A, B, C, D statements are correct. Therefore option B. This is all about lanthanoid contraction. Covalent properties increases, chemical reactivity decreases, basic nature also decreases, and for 4D to 5D series, atomic radius or size remains constant. So about E, separation will be very difficult due to similar size. A, B, C, D statements are correct. Next one. About nature of oxides. So metallic oxides are basic and non-metallic oxides acidic. Here 5 oxides are given: Li2O, BeO, B2O3, CO2 and N2O3. See, Li2O is metallic oxide which is basic. BeO, amphoteric oxide. Remaining B2O3, CO2, N2O3 are acidic. And between boron, carbon, nitrogen, from boron to nitrogen, acidic nature increases. N2O3 will be most acidic. So clearly option D. First N2O3, next CO2 carbon dioxide, next B2O3 which is boric anhydride, next PuO amphoteric, and last Li2O is basic. Decreasing acidic nature. Next question. Correct order of first ionization energies of following elements. So here clearly second period elements are given. In case of second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These are the elements. So clearly, in a period from left to right, ionization energy generally increases. It's like this. This is expected order. Expected order. But actually, this is NS2 configuration. This is NS2NP1 configuration. Next, for nitrogen, NS2NP3, and for oxygen, NS2NP4. In these two cases, order will be reversed. So therefore, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Take here order. Lithium to beryllium as usual increase, but beryllium to boron decrease. Order will be reversed. Next, boron to carbon increase. Carbon to nitrogen increase. Nitrogen to oxygen again decrease. Anomalous pair. Next, increase, increase. So based on this, we can arrange. So out of given elements, first nitrogen will be having more. Nitrogen. After that, beryllium. Next, boron. Next, lithium. This increasing order of IE1, first ionization energy. For option A. Remember this order, very, very important. Beryllium to boron, nitrogen to oxygen, ionization will be reversed. So that is based on configuration. Beryllium completely filled orbitals and nitrogen half filled orbitals. Next one. The orbital with 4 radial and 1 angular nodes is. Here I am taking 6 beached orbital. So this is common question for atomic structure and periodic table. So number of radial nodes equal to n minus L minus 1. So n is here 6 minus for p orbital L equal to 1 minus 1, that is 4. Next, angular nodes. Angular nodes equal to just L. L value 1. Therefore, option B. For remaining options also you can check. Six beached orbital has 4 radial nodes and 1 angular node. Next, which are the following options? They presents the correct ionic radii in N3 minus, O2 minus and F minus. N3 minus, O2 minus and F minus. These are isoelectronic. Isoelectronic species. Atomic number 7, 8 and 9. So atomic number increases in this order, but size will be in this order. In case of isoelectronic species, as the atomic number increases, size decreases. Therefore, size order N3 minus, O2 minus, F minus. The N3 minus will be having more size. Therefore, check options. First, large value should be there, 1.71. Next, middle, intermediate value, 1.4. At the end, 1.36 least value should be. Therefore, option C. This is also common question for atomic structure and periodic table. atomic number versus size in case of isoelectronic spaces. Or we can say as the negative charge increases in case of isoelectronic spaces, the negative charge increases, size also increases. In this way also you can remember. In case of only isoelectronic spaces. Next one. So here first ionization energies of 4 consecutive elements of second period are given. The first ionization energy of nitrogen. So here given values belong to carbon, nitrogen, oxygen and fluorine. These are successive elements and ionization energies we know. First ionization energy order. Carbon to nitrogen as usual increase. Next, between nitrogen and oxygen that will be reversed. Remember this. Oxygen to fluorine again increase. Take here values 1086, 1402, 1314 and 1681. So clearly 1402 is ionization of nitrogen. These are second period elements. So nitrogen P3 configuration half filled and this is P4 configuration. Carbon to nitrogen increase. Next nitrogen to oxygen decrease and again oxygen to fluorine increase. Only one anomalous pair due to half filled configuration of nitrogen. Therefore option B. Important question. Next one. Among the following pair of elements having same electronegativity values are. So we know hydrogen 2.1, phosphorus also 2.1. That means option 1. Next, in 2. Beryllium and aluminium diagonal pair. So diagonal pair will be having similar electronegativity value. In case of diagonal pair, no need to check values. Beryllium and aluminum will be having similar electronegativity value. Therefore, these will be having diagonal relationship. Next, third. Nitrogen 3, chlorine also 3 value according to Pauling scale. Next, fourth, carbon 2.5 and phosphorus 2.1. Different values. Therefore, options 1, 2, 3 are having same electronegativity values. So, option A. This is also important. So, diagonal pair of elements will be having similar electronegativity. No need to check values. For remaining elements, remember these values. Very, very important. Next one. The successive ionization energy values are given. First ionization, simply I1 410, I2 value 820, I3 value 1100 I4 value 1500 and I5 value 3200. Observe the gap. I1 to I2 small gap, I2 to I3 somewhat small gap. Next I3 to I4 again small gap. Next between I4 and I5 large gap or jump. Large jump between I4 and I5. So therefore there should be 4 valence electrons. It is very difficult to remove fifth electron. Therefore there should be 4 valence electrons. 4 valence electrons means fourth A group or 14th group element. So therefore there should be 4 valence electrons. Option B. This model is very important. So number of valence electrons depends on the gap between successive ionization energies. Next one. This is also very important question. Enthalpy of atomization. Remember like this. Atomization directly proportional to metallic bond strength. Heat of atomization or enthalpy of atomization directly proportional to metallic bond strength. As the bond between metal and metal increases, heat of atomization also increases. So for s block elements, so down the group, that means top to bottom, metallic bond strength decreases. For s block elements, top to bottom, that means down the group, metallic bond strength decreases. Therefore, enthalpy of atomization decreases. For p block also similar. Same top to bottom, metallic bond strength decreases. Or force of attraction decreases. Next for p block elements, top to bottom metallic bond strength increases due to lanthanoid contraction. Due to lanthanoid contraction. Say clearly. So in option A, enthalpy of atomization decreases from top to bottom in case of s block elements, which is correct statement. Next, here we have to identify incorrect statement. Next, enthalpy of atomization decreases down the group in p block elements. That is also correct. In case of D block, enthalpy of atomization increases down the group due to lanthanoid contraction. Size will be decreased. As the size of element decreases, metallic bond strength increases. So in a 3D to 4D series, size increases, and 4D to 5D, size constant, remains constant. And Z effective increases. So due to increase of Z effective, there will be more metallic bond strength. Enthalpy atomization increases. So therefore option C. In case of D block, enthalpy atomization should increase due to lanthanoid contraction. 3D to 4D series size increases, but 4D to 5D size remains constant, and moreover effective nuclear charge increases from 4D to 5D. Metallic bond strength also increases. So enthalpy of atomization is not regular in case of d block elements. 3D to 4D decreases, but 4D to 5D increases. Next question. This is also common question for atomic structure and periodic table. Here we have to arrange given species in decreasing order of radius. Here first write more negative value P3 minus, after that S2 minus, next 1 minus, neutral, unipositive and dipositive. So these are anions, and this one neutral atom, and remaining two are cations. All these are isoelectronic species again. Isoelectronic species. Write atomic number 15, 16, 17, 18, 19 and 20. So in this direction atomic number increases, size will be reverse. Therefore size order P3 minus highest, next S2 minus, Cl minus, argon, K plus and Ca2 plus. Therefore option A. This is also important. Anions, neutral atom and cations combination. Or we can say like this. As the negative charge increases, size increases. This is one point. Next, as the positive charge increases, size decreases. In case of isoelectronic series, P is having more negative charge. Next question. Common oxidation state of F-block elements is 3. For F-block elements, common oxidation state plus 3, or we can write Roman number 3. But for some elements, plus 2 and plus 4 will be stable based on configuration. So what are the elements? Europium. Europium, write configuration, electronic configuration, xenon core 4f7 6s2. So with removal of 2 electrons, these 2 electrons, it becomes Eu2 plus, and the configuration will be xenon core 4f7. So which is half filled. half-filled stable. So due to F7 configuration, this can exhibit +2 oxidation state also. Next for terbium, configuration TB, xenon core 4F9 6S2. So remove here 2 electrons and here also 2 electrons. Therefore, we'll get Tb4 plus xenon core 4F7 6S0. This is also half filled and stable. Therefore, the other oxidation states of europium, terbium are +2 and +4. Therefore, option A. Most common state is +3, but some elements can exhibit +2 and +4 based on configuration. If europium loses 2 electrons, it will be having half-filled configuration, which is stable according to Hund's principle. Terbium, after losing 4 electrons, it becomes 4F7 half-filled, that is also stable. Europium +2 stable, terbium +4 stable. Other oxidation states are +2 and +4. Or we can say Roman numbers 2 and 4 oxidation states. Next one. So very important. Which are the following statements about BF4 minus and Al I6 minus, or we can write where I must be there, or F. We can take F. I am changing here compound. Al F6 3 minus. This will be the compound. So what are given? BF4 minus and Al F6 3 minus. So first calculate oxidation state. Here it is having +3 and it is also +3. So oxidation state is same. Therefore, first option wrong. So in first option, boron and aluminium differ in their oxidation states is given, but here same oxidation state. This is about first option. Second option, covalency. For boron, covalency is maximum number of bonds around boron. So 4. For aluminium, covalency is 6N. 6 fluorine atoms are surrounding aluminium. Boron and aluminium differ in their covalency. So this is correct statement. Next, third. So BF4 minus obeys octet rule. That means around boron, 4 bonds are present. 4 bonds means 8 electrons. But around aluminium, 12 electrons will be there. Next, fourth. Beryllium and aluminium can show diagonal properties. Here boron and aluminium are given. That is wrong. So statement 2 is correct and 3 is correct. Therefore option D. First related to oxidation state, Next covalency, maximum number of bonds. Next octet rule. Next diagonal properties. So there is diagonal relationship between beryllium and aluminum, not boron and aluminum. Second and third statements are correct. Next one. So which of the following is most basic oxide? So these are central atoms here: sulfur, selenium, polonium and tellurium. Oxygen, sulfur, selenium, tellurium, polonium. This is 16th group or 6th A group. So down the group, metallic nature increases. That means simply polonium is most metallic. You know, metallic oxides are basic in nature. Metallic oxides, basic in nature. Therefore, POO, polonium oxide is most basic. Option C. In any group from top to bottom, metallic nature increases. So basic strength of oxides directly proportional to metallic nature. Polonium has most metallic nature, therefore most basic oxide. Polonium oxide. Next one. So electronic configuration which is associated with highest first ionization energy. Here check stability of configuration clearly. So option A 3s2 3p2. Next option B 3s2 3p3. Next 3s2 3p4, 3s2 3p1. So clearly option B has neon core 3s2 3p3 configuration. This is completely filled and P3 half filled. Both are stable. Completely filled obviously stable due to spin pair up. Half filled is also stable due to exchange of energy between unpaired electrons according to Hund's rule. Therefore, it is very difficult to remove electrons from half filled or completely filled configurations. Therefore, option B. Simple question only, but very, very important. Next one. The set of amphoteric oxides among the given. Amphoteric oxides. I will add here. Beryllium, aluminum, zinc, tin and lead can form amphoteric oxides. Beryllium, aluminum, zinc, tin, lead can form amphoteric oxides. So check here options. ZnO, PbO. So in case of beryllium, only one oxide is present, BeO. In case of Al, Al2O3. In case of zinc, ZnO. In case of tin, two types of oxides, SnO, SnO2. In case of lead, also two types, PbO, PbO2. These are amphoteric oxides. Check here options. ZnO, PbO, SnO2 are present in B option. Therefore, all are amphoteric oxides. Lead monoxide, lead dioxide, tin monoxide, tin dioxide. Next, Al2O3, alumina, BeO, beryllium oxide. All these are amphoteric. Next one. In which of the following elements, aluminium, boron, magnesium, potassium, are correctly arranged in increasing order of their metallic nature? See here, S block elements are most metallic. They can lose electrons more easily due to loss of electrons. See here, S block elements in given elements, potassium, most metallic. Next, after that, magnesium also given. These are S block elements and most metallic. So this is 1A group element and 2A group element. So between 1A and 2A, metallic nature more for 1A. Metallic nature order. So between potassium and magnesium, potassium will be having more metallic nature. Next, after that, P block. Less metallic. That means you can say most of the elements are non-metallic in case of P block. So P block contains metallic, non-metallic and both metallic and non-metallic, that is semi-metals. So P block elements are boron and aluminium. So between boron and aluminium, these are third A. This is also third A. When compared to boron, aluminium is more metallic. I will write here. Next, between S block and P block, S block more metallic when compared to P block. Now compare the elements. First take S block elements, potassium and magnesium. Between magnesium and potassium, potassium more. Next, P block elements, boron and aluminium. When compared to boron, aluminium is more metallic. Therefore, option A. So this type of questions very important. Orders, metallic nature, non-metallic nature, valencies. Next question. In which of the following elements are arranged in correct order of their electron gain enthalpy? Electron gain enthalpy values. See here 4 elements are given. Nitrogen, oxygen, fluorine and sulfur. Nitrogen, oxygen, fluorine and sulfur. So fluorine is most electronegative, Most electronegative means it will be having more electron gain enthalpy. That is more negative value of electron gain enthalpy. So after that, sulfur has large size and these two are small. So nitrogen and oxygen, due to small size, they cannot accept electrons easily. So when compared to N and O, sulfur can accept. Next, between N and O, this is more electronegative. Therefore, oxygen can accept electrons easily. Or we can compare group wise or period wise. So NOF. NOF is period. In period from left to right, electronic enthalpy increases. So therefore, option will be A. First fluorine, next sulfur, next oxygen, next nitrogen. Next one. Next question. Lithium shows diagonal relationship with X and aluminium with Y. X and Y respectively are. Here first lithium, second period, lithium, beryllium, boron, third period, sodium, magnesium, aluminium. So these two are diagonally related. Next I will add carbon also, carbon and silicon, beryllium, aluminium, boron and silicon. These are diagonal elements. Lithium shows diagonal relationship with X, that means magnesium. First magnesium should be there. Next aluminium with beryllium. So here magnesium and beryllium, option A. So group numbers, first A, second A, third A and fourth A. Group numbers. Next. This is also related to isoelectronic species. Atomic radius. S minus 2 to, here we know S 2 minus and Cl minus. These are isoelectronic. So more negative charge means more size. S minus 2 has more size when compared to Cl minus. Check options one by one. There is decrease from S minus 2 to Cl minus. Next one more. K plus and Ca2 plus. So K plus and Ca2 plus again isoelectronic. So K plus has more size. So as the negative charge increases, size increases. As the positive charge increases, size decreases. In this way we can compare. So decrease from S minus 2 to Cl minus and increase from K plus to Ca2 plus is given. Therefore option A wrong. Next B. An increase from S minus 2 to Cl minus, that is also wrong. C. Significant decrease from S minus 2 to Ca2 plus. I will club these two. S2 minus, Cl minus, K plus and Ca2 plus. This is the order, decrease. So in this direction, atomic number increases, therefore size decreases. Size order, decreasing order. Largest size S2 minus, smallest Ca2 plus. Therefore option C. Next one. Simple question only. The first ionization energy of beryllium is greater than that of boron. So beryllium configuration NS2 we can write, boron NS2 NP1. It is very easy to remove NP electron. Therefore, first ionization energy order. Beryllium highest. So option Assertion A is correct. Next, 2p orbital has lower energy than 2s orbital. That is wrong. For 2p, n plus l value 2 plus 1, 3. Next, 2s, n plus l value 2 plus 0, 2. So more n plus l value, that means n plus l value increases, energy also increases. So energy is more for 2p, less energy. So therefore, reason wrong. Option C, A is true, R is false. Assertion true, reason false. Next one. The correct order of electronegativity of carbon in various hybridizations. Here sp, sp2 and sp3. So electronegativity directly proportional to percentage of S character. Very, very important. So here percentage of S I am writing 50%. Here 33.33% and here 25%. So in this order, percentage of S character increases. Therefore, electronegativity also increases. Therefore, electronegativity order Sp, Sp2, Sp3. This will be the order. So option B. Electronegativity depends on percentage of S character. Next one. Which of the following statements is incorrect? I will explain option wise. Option A. TL plus 3 always changes to TL plus 1, 1 plus due to inert pair effect. Inert pair effect. That means TL3 plus is reduced. Therefore, oxidizing agent or oxidant. Option B. Ga plus 1 changes to Ga3 plus. So plus 1 to plus 3 means oxidation. Therefore, that will be reductant. Next to C. Pb plus 4 changes to Pb plus 2 due to inert pair effect. So plus 4 is reduced to plus 2. Therefore, oxidant. Next D. As plus 5, that is stable. There is no change from plus 5 to plus 3. Plus 5 is stable. No reduction. Common oxidation state is, I'll write once again, As plus 5 changes to plus 3, but this is non-spontaneous process. Plus 5 is stable, therefore no change, no reduction, therefore not an oxidant. See here, TL3 plus 2 plus 1, reduction, reduced. Reduced means oxidizing agent. Ga plus 1 to plus 3, oxidized, therefore reducing agent or reductant. Plus 4 to plus 2, reduced, oxidizing agent. So there is no change from plus 5 to plus 3 because plus 5 is stable for arsenic. Therefore, there will be no reduction, no oxidation. Therefore, incorrect option is D. So, Tl3 plus is oxidant, Ga plus 1 reductant or reducing agents, Pb plus 4 oxidants. But As plus 5 are not oxidizing agents due to no conversion. No conversion from plus 5 to plus 3. As5 plus will not be reduced. Therefore, that is not oxidizing agent. Option D. Next one. So, Mulliken scale of electronegativity. Electronegativity on Mulliken scale equal to ionization energy plus electron affinity by 2. Average of I and A. When IE and EA are in electron volts per atom. Therefore, IE value 13 plus EA value 4 by 2. 17 by 2, which is 8.5 electron volts. Not electron volts, electron negativity 8.5. No need to write electron volts. Removing V. Just value is 8.5. Mulliken scale of electronegativity 8.5. So option will be A. 8.5. Next one. Calculate the energy required to convert all atoms in 4.8 grams of Mg to Mg2 plus. Here Mg to Mg2 plus means we have two processes. First Mg to Mg plus, next Mg plus to Mg2 plus. This is first ionization and second ionization. So total conversion Mg to Mg2 plus is I1 plus I2, which is total ionization energy. So here I1 value 740 plus 1450 kilojoules per mole is given. So what is this value? 740 plus 1450. 2190 kilojoules per mole. Per mole means here 1 mole of magnesium will be equal to 2190 kilojoules. So 1 mole of magnesium means 24 grams equal to 2190 kilojoules. Therefore 4.8 grams will be equal to how much? Say this is x kilojoules. So from this x value will be equal to 2190 into 4.8 by 24. So which is equal to plus 438 kilojoules. So option D. So for the conversion of 4.8 grams of Mg to Mg2 plus 438 kilojoules of energy is required. Next one. Second ionization energies of lithium, beryllium, boron and carbon. Lithium, beryllium, boron and carbon. So after first ionization, after I1 changes to Li plus, Be plus, B plus and C plus. So second ionization energy I2 Li2 plus, Be2 plus, B2 plus and C2 plus. So after removing one electron, Li plus becomes, or Li plus, helium configuration will be there, most stable due to noble gas configuration. Therefore, second ionization will be very high. Next, boron becomes beryllium configuration. After removal of one electron, boron becomes beryllium configuration. That is also stable configuration. After that, carbon and beryllium. So option will be B. Just compare Li plus and B plus. Li plus configuration is helium configuration. B plus configuration is beryllium configuration, which is NS2. NS2 configuration completely failed. Therefore stable. Next one. Choose the smallest ion. So as the positive charge increases, size decreases. As the negative charge increases, size increases. See here, Mg2 plus has more positive, therefore size will be very small. Option A, simple. Next one, 4 elements with atomic numbers Z minus 2, Z minus 1, Z and Z plus 1 are given. These are isoelectronic species. So atomic number increases in this order, therefore size increases in this order. Therefore the atomic number of an largest size is Z minus 2, obviously. This is side order. As the atomic number increases, size decreases. Atomic number lowest Z minus 2, therefore size will be more. Option A. So this is about worksheet questions of periodic table. In next video, we will discuss one more topic. All the best and thank you.